Hi everyone, welcome to the second lecture of the Module 4 about electric flux and Gauss's law. So Gauss's law is an alternative way and the easy way to find the electric field. So what you see from this slide, okay, is this are the electric fields of many forms. So we got the one that is a uniform electric field, and we got the electric field from point charges that flows through the surfaces. Okay, so if I say that these blue regions are the closed surface, we try to define the flux as the electric field and times by the surface area. So that if we talk about electric flux, in this case, it would be different from this case. And we are going to learn about this, learn about how significant on defining the closed surface. So the outline, we start talking about the definition of electric flux. Then we try to relate the electric flux to Gauss's law, and we do some examples to find the electric field of the electric fields of the point charge, the line charge, of the plate, and of the parallel plates. And then we are talking about using Gauss's law to find the electric field in the conductor and in the insulators. Okay, electric flux. Let's start with the definition. If we consider the electric field of the intensity E that pass on the area A. So the area A is in the red and the electric fields are the E. So, so we can change the amount of field lines passing the area by either rotate the area by the angle theta or change the intensity of E. Okay, so as you can see the lines, the field lines in green. Those are the part that is passing the area in red. Okay, so the green are passing and the yellows are not passing. Okay, so changing the angle or changing the area, as we do now, you change the number of field lines that passing through the areas. And in the other ways, if we reduce the intensity by expanding the field, that reduce the intensity, there are less number of field lines that crossing the regions. So that we define flux as the intensity and times by the area and times by the cosine of the angle, as we can see from this equation. Okay, so the full definition of the flux is the integrate of E dot A, in which A is the vector of the area that is perpendicular to the surface. And if you do the dot product of E, we are going to consider just only E that is in perpendicular. Okay, so perpendicular is tangcha, yeah, perpendicular direction to the area. So if E is parallel or not perpendicular, we are not counting the flux. But if E is passing directly to the area, and if E dot A is perpendicular, so if E and A same direction, we count the electric flux. Okay, so to simplify the case, if we consider the case that E and A are parallel, okay, so in this case, E and A are parallel, we just change the definition from E dot dA to E times dA, because cos theta is cos 0 and cos 0 is 1. And the further simplification, if E or electric field is a constant, we just simplify the integral here into the product between E and A. Okay, so let's consider some cases of electric flux. Okay, so if I look at this case of a uniform electric field, if vector E or electric field is perpendicular to the area, or if E is parallel to A, or if A is the vector that is perpendicular to the area. So if E and A parallel, phi or electric flux will be simply EA. But if the area is inclined, when the area is inclined and the vector A is making the angle theta making the angle theta with E, we found that flux is E times by the cos theta. So or if I say that if we rotate the area in blue by the angle theta, the flux will change from EA to EA cosine theta. But if we rotate the area so much, and the area and electric field is parallel, and the vector A and the vector E is perpendicular, we found that the flux is zero, okay? Or no field lines pass the area, so flux is zero, okay? So we are going to do the examples, okay, in the example class. So in which I'm going to talk about this a little bit. So we have here we have here the shape of a prism, okay? And from this prism, the prism is placed within an electric field. And at the first place, in part A, we consider the field that coming through the area at the back, in which we see that the area at the back is perpendicular to the field. So when the area is perpendicular to the field, like this, we can use the electric flux as E times A. Okay, and then you can also see the negative sign, negative notation. So the negative notation denotes the flux that is coming in. So we use negative sign for the flux coming in, and we use positive sign with the flux going out. Okay, so in part B, they ask for the flux through the inclined surface, or the flux coming out from the inclined surface. So that's we use the positive sign, and we use the EA cosine theta, in which theta is 60 degrees, and then we can find the flux that coming in and going out. And then finally, we can show that the flux through the whole object is zero, because if we look at this problem from sideways, the flux has come in, or electric field lines has come in through the vertical surface and come out from inclined surface. So that come in for one line and come out for one line. But if I consider another few lines, it come in and go out the same number. Okay, so now it come in 4 times, come out 4 times, and number of flux in and number of flux out are equal. So that the flux through the whole object should be 0. So Gauss's law. Now, how are we going to apply the concept of electric flux in calculating the electric field? Okay, so the Gauss law says that when a closed surface is in a region with an electric field, the net flux is determined from the difference between number of field lines going out. So as I said, going out is using positive, and coming in is using the negative sign. Okay, so Gauss law says that the net flux through the closed surface. So net flux means that you need to add up the flux going out and the flux coming in. Okay, plus minus. So the net flux is equals to net charge divided by the constant epsilon 0. Okay, so from this example, okay, I say that okay, the flux in is equal to flux out, and the net flux is 0. So when net flux is 0, that means no charge within the region, within the area. Okay, so to see this a little bit more clearly, okay, so we are going to say that if there are electric fields, coming out from this closed surface, so we say that this is a closed surface, and then we can find that the net flux of this closed surface is E times A, integrate E times A. So we can say that if the net flux here is positive in this case, so we can say roughly that within these regions, there should be the charge inside or Q in. Okay, so for example, okay, so let's try to find the electric flux through a cube with using Gauss's law. Okay, so from this example, we see that the charge Q1 is within the cube, and the other charge Q2 is without the cube. So they ask us to find the electric flux to the cube surface. So if you want to find the electric flux, one way is to use the integration. So you need to find, okay, electric field, many electric field, and you need to integrate. Okay, you might need to integrate the electric field through the area. So the integrate here is difficult. Okay, so it's not easy to do this integration. So, but your life will be a lot easier with the Gauss's law. So with Gauss's law, we can say directly that the total charge inside, or Q in, which is actually the Q1 in this example, which is actually Q1. And if we substitute the Q1 and the epsilon 0 or this constant, we'll be able to calculate the electric flux without the integration. So we can calculate the flux from here. But what about Q2? Q2 is not used here because Q2 is outside. So we are not used Q2 for calculated flux. Okay. Okay, so another example to test your concept, okay? So we are also doing this example again. So I'm going to talk about this pretty roughly. So we have the system of charges, minus 2q. Oh, sorry. We are going to look at this system of charges. So we have minus 2q plus q minus q. And we try to define many surfaces, range from S1, S2, S3, S4, and we want to find electric flux through the surfaces S1, 2, 3, and 4. Okay. So what we do here is we try to consider the surfaces one by one. For example, if I consider the surface 1, the surface 1 here, so, or this area. So you can see that from this surface, okay, so Q in is the total charge inside. The total charge inside is minus 2q and plus 1q. So that would be minus q over epsilon 0. And then when we substitute the q value, or 1.6 nanocoulomb, we are able to calculate electric flux through S1. Okay, and then if I try to do for the other surfaces such as Q4, so Q4 over here, so there is no charge inside whatsoever. So that Q in of the S4 is 0. So that is electric flux 0 for Q4. Okay, and then this example is a little bit tricky. That they want you to calculate the flux through the plate. Okay, so if we want to calculate the flux through the plate, so we need to know that for a charge Q, positive charge Q, it will generate electric field E, and electric field E will pass through the area created by the square, or so that the area will be d square. Okay, so if we want to find the flux directly, we have the direct definition of electric flux. Okay, which is also not easy to find. Okay, and using Gauss's law might also be hard because this one is an open surface, not a closed surface. Okay, but we try to do some trick here that that instead of we looking at just only one side of the surface, we assume that there is a cubic. Okay, there is a cubic around the charge, and the charge is at the center of the cubic. So when the charge is at the center of the cubic, so if I say that this is the area 1, this is the area 2, 3, 4, 5, and 6 at the top. So I can say that the flux through the area 1 is equal to the flux through the area 2, and is equal to 3, 4, 5, and 6. Okay, so that's the total flux in the system would be equal to 6 times the flux through 1. So what I do is I just need to find the flux, the total flux through the cubic. Okay, so if I assume that this cubic here is a closed surface, I will say that this one is a flux through the cubic, and the charge within the cubic is Q. Okay, and then the flux through just only one phase. Okay, that would be 1/6 of the charge through the whole cubic. So that would give you the answers. Okay. Then the other applications of Gauss's law to find the electric field from some shapes, some simple shapes. Okay, so we are going to go through these steps. So the step 1, if we first trying to use the Gauss's law, what to do is we are going to draw electric field vectors from the object. Okay, so try to make the picture. So if I have a charge, I draw electric field vectors, and then draw a closed surface or a Gaussian surface. Okay, and the condition, what is special for the Gaussian surface to make the calculation easy, okay, is electric field vectors with uniform intensity. Okay, so we can see from the spherical shape that it now has the uniform intensity, and the electric field should also perpendicular to the surface. Okay, so that's when with uniform and perpendicular to the surface, we can then simplify the flux as E times A. Okay, so you need to define the Gauss surface so that the flux can be approximated as EA. So that's the trick. Okay, and then find the Q within the surface, in which in this case is Q, and then we can use the relationship to find the electric field after that. Okay, so we start with some simple shape. Okay, such as the sphere that I show you already. So we start with drawing electric field lines. Okay, so here are the electric field lines. Okay, and then we draw a Gauss surface. So the Gauss surface is in blue. Okay, and then let's check if the field vector is perpendicular to the Gauss surface. Okay, if we choose the sphere, the answer is yes. But if we choose the other shapes like this, if we choose the other face like this, and electric field lines is like this. Okay, so this is not perpendicular. So we are not using this surface. So we choose the spherical surface because all vectors perpendicular to the surface. And also, field vector is with uniform intensity. Okay, so that if the field is not uniform, also difficult to do. So that's on the left-hand side. Okay, it would be simply phi equals EA. If these two conditions are true, phi will be equal to EA. And that A, the area, in the case of the sphere, this area of the spherical surface is 4 pi r squared. And then the Q in, okay, is just plus Q. Okay, so we can prove that E is equals to Q over 4 pi epsilon 0 r squared. So this is equals to Coulomb's law. Okay, because in Coulomb's law, we have F equals K QQ over R squared, and we have F equals QE. So E will be KQ over R squared. So, and K is 1 over 4 pi epsilon 0. So we can show that Gauss's law can be used in place of Coulomb's law in some cases. Okay, and for the line charge, okay, so this is the electric field from line charge. Okay, so every field lines come out perpendicular from the line. Okay, so how to find it? And in line charge, we are going to choose the Gauss surface as a cylinder. Okay, so the cylindrical Gauss surface. So let's check if all of these conditions are true. So field vectors from the cylinder, is that perpendicular? Yes, it is perpendicular to the Gauss surface in every place. Okay, and is it with uniform intensity? It is. Okay, because if you look from the sideways, okay, so suppose that this is a circle and these are electric fields, intensity are the same. Okay, so that's flux can be found from E times A, and A, or the area of the cylindrical curved surface, would be 2 pi r, or the circumference, and times by L, or the length of the cylinder. And then for Q in, it can be written in terms of the charge density times by the length, because the charge density here is already the charge per length. Okay, so that the charge Q in can be written in terms of lambda L. And finally, we can find that the electric field E can be written in this term. Then another case is about the charge plate. For the charge plate, we are going to pick the Gauss surface as a prism with cross-section area of A. So field vectors, they are all perpendicular to the surface, and also uniform. Okay, so that we can use this Gauss surface. So so when we use Gauss's law, now we know that the flux can be written in terms of E times 2A. So why is this 2 appear? Okay, because it is because we are considering electric fields that come out in both sides of the plate. So the first side, it has the area A of the Gauss surface, and the other side, it also has another area A of the Gauss surface. So the total area would be 2A. And finally, we should find that the electric field E is in terms of the sigma, or the charge per area, and and the epsilon 0. So on the right hand side, the Q in over here can be written in terms of sigma A, because when Q in is because Q in is the charge, and the sigma is a charge per area. So when sigma times A, it will give you the charge. Okay. So that from Gauss's law, we start with finding the flux. Okay, and then finding the electric charge inside, which is sigma A. And finally, we can easily derive for the electric field about electric field that is generated from the plate. Okay. Then, when consider the case of parallel plates, okay. So if I bring a plate with positive charge on it, okay, and it generates electric field in this direction, so I can say that if this guy has a charge density of sigma, okay, and so the electric field would be sigma over 2 epsilon 0 from Gauss's law. And then if I bring another plate but with negatively charged on it, okay, so with negatively charged, the direction of electric field will be coming into the negative charge, okay, and then the magnitude of electric field would be the same, okay, but when I try to bring these two together, what you see is that for the positively charged plate, electric field in blue, okay, one will go into the right hand side direction and one will go to the left, okay, and then when we place the negatively charged plate 2, okay, so we can see that for the region here between the plate, okay, you can see that the electric field from the first plate is also go to the right, and the electric field from the right hand side, or from the negatively charged plate, is also going to the right, okay. So that's we have the field that is composed of E from positive charge and another E from negative charge. Okay, we have, okay, sorry. Yeah. We have E from positive charge, and we have another E from negative charge. Okay, so that's here, we should have the electric field of 2E between the plates. But outside the plates, you can see that E from the positively charged plate is go to the left, and E from negatively charged plate is go to the right. So that the total electric field here is 0. And also the total electric field here on the outside is 0, okay? So, so that's for the electric field between the charge plate, between the plate of the charge Q and minus Q, okay? It would be the electric field from a single plate. So this is from one plate. Okay, and also the electric field from another one plate added up together to be sigma over epsilon 0. Okay, so that was in that case. So then for the case of spherical conductor, for a spherical conductor, electric charge is distributed on the surface, okay, on the surface only, and there's no charge within the volume, okay? So if you recall what we have discussed before about the conductor, for the conductor, charge can move freely within the conductor so that it repel each other, the charges repel each other, and we end up with charge being on the surface and there is no charge here within the volume. Okay, no charge within the volume. So that's if we try to use the Gauss law to find the electric field inside and outside. Okay, we can use the Gauss's law for that. Okay, and you find that finding electric field is easy. Okay, so for the outside regions, okay, let's consider first the outside regions. I consider the Gaussian surface. I consider the Gaussian surface outside, and with using the sphere. Okay, on the left hand side of the Gauss's law equation, I'm going to have the EA, and A is 4 pi r squared. And then on the right hand side of the equation, okay, what is the Q in? Okay, so the Q in here is the total charge within this volume. Okay, the total charge within the volume. We found that it is the total charge of the system, or Q. So that's, in this case, the Q in is Q. Okay, so that's for the electric field outside. We also found that it is Q over 4 pi epsilon 0 r squared. Okay, so the same as the case of the point charge. Okay, but if I try to find the electric field inside, okay, now for the inside region, I need to create the Gauss surface inside the region. Okay, and what difference here is on the left hand side. Okay, I should have flux equals EA and equals E times 4 pi r squared as usual. Okay, but then if I consider Q in, okay, so the charge inside this region, okay, what would be the charge inside this region? The charge here is 0. Okay, why it is 0 for the conductor? Because for the conductor, all charges are at the surface, and there is no charge in the volume. Okay, so when I create the Gauss surface anywhere within the volume, I found that the charge inside is 0. So that on the right hand side of this equation will be 0, and the electric field within the conductor will always be 0, or no field within the conductor. Okay, so in summary, okay, for the conductor, we have, if we put the Gaussian surface outside the conductor, the charge inside still be Q, and we found that the electric field has a non-zero values and will be likely to be Coulomb's law. But if I place the Gaussian surface inside the conductor, the Q in, okay, the Q in from Gauss's law is 0. Okay, so that leads to the 0 electric field. Okay, then if I draw the graph of a spherical conductor to find the electric field as a function of R, so we can see that electric field within the region, within the conductor, will be 0, stay 0, and then the electric field outside the conductor will be perpendicular to inverse R squared. Sorry, will be proportional to inverse R squared. Okay, so that we have the function that look discontinuous. So we have we need to consider the region inside or less than R, okay, and outside or more than R separately. Okay, so the applications of this principle is about Faraday cage. So if you want to shield any objects from the electric field outside. So if we want to shield things from lightnings, we are going to use the surface of the vehicles as a conductor. Okay, so as a conductor, you're going to be safe from the electric field. Electric field cannot get inside you, and you'll be safe. Okay, then we consider the case of insulator. In the insulator, as opposed to the conductor, for the conductor, we see that the charge will be just only on the surface, and there will be no charge here. But as an insulator, the charge is distributed within the volume. So there are charge here, 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 and there are charge everywhere in the volume. Okay, so the calculations of electric field using Gauss's law will be different. Okay, so in the outside region, it is the same. It is the same as the case of conductor. Okay, it is because if I draw the Gauss surface outside the regions, okay, I still find that the total charge is Q anyway, and when I use the Gauss's law, electric field times area, and having Q in as Q, you still get the same function of electric field. But for the inside regions, now it becomes a little bit tricky now, because when I try to draw the Gauss surface inside the insulator, okay, so this Gauss surface has contained some amount of charge Q in, okay, so that's in order to find the Q in, you need to use the ratio between the whole volume, okay, and then you divide the ratio of the small volume. Okay, so if you get a small volume, divide the whole volume and times by the whole charge. Okay, you're gonna get the charge of the small volume. Okay, so that's to find the ratio of the charge within. So that finally you end up with this Qn as R squared over big R squared over Q. So, and that is certainly less than the whole charge. Okay, then I plug this into the Gauss's law. So for the Gauss's law, again, on the left hand side, I times electric field with the area A, of the sphere, and then I use the expression of Q in from the last slide. Okay, so this is the Q in from the last slide. I plug it into the Gauss's law. Then we come up with this expression of E, and we found that if we cut all other constants, we find that E is proportional to R. Okay, so so that's with these two cases, the case of outside regions, we found that E is inverse proportional to R squared. But the case of inside, we found that E is proportional to R and is the linear function. Okay, so that's the different pictures that we see between the conductor. The conductor, we see no field at all. Okay, but for the insulator with uniformly distributed charge, we see that the electric field inside the spherical insulator increase as a linear function and then decrease as the inverse R squared function.